What will happen to the iron filings when current passes through this straight conductor? The iron filings will arrange like this. These are the lines of the magnetic field created when current passes through the straight conductor. What happens to the strength of this magnetic field when current increases? The strength increases. Or can the strength be increased without increasing the current? One way to increase the strength of the magnetic field without increasing the current is to use a circular coil or loop. Let us look at some of the advantages of circular coils. Just as in the case of a straight conductor, the field lines are in the form of concentric circles near the wires. But towards the center of the coil, the field lines become almost parallel, making the field in this part uniform. In other words, the magnetic field is stronger near the conductor. This strength decreases as you go closer to the center of the coil. How can greater magnetic field be generated around the circular loop? You can generate a greater magnetic field by reducing the distance between the two curves and by having more turns of the coil. How can you determine the direction of the magnetic field in a coil? Will the right-hand thumb rule work in this case also? In a straight conductor, the north pole of the compass needle shows the direction of the field lines. If you know the direction in which the current is flowing, you can find the direction of the field lines by using the right-hand thumb rule. In a circular coil, the clockwise direction of the current flow indicates a south polarity. And vice versa. The Maxwell's corkscrew rule is used to determine the direction of the magnetic field lines. Imagine that you are using a corkscrew, the same way as you would to close the cork of a bottle. The direction in which the corkscrew is moving is the direction of the current. The direction in which you turn the corkscrew is the direction of the magnetic field that is formed. When talking about a circular with many coils, how many turns is practical? An insulated copper wire can be coiled cylindrically like this. And what we get is a solenoid. Look at the pattern of the magnetic field lines running around a solenoid carrying current. We can increase the strength of the solenoid further by increasing the number of loops. Let's see how. Each loop in the coil contributes additional strength to the magnetic field. So, the more the loops, the stronger the field. And as a result, the magnetic field lines become denser. How will you determine the north and the south poles of a solenoid carrying current? The solenoid carrying current behaves almost the same as a bar magnet. One end of the solenoid is the north-seeking pole, and the other one is the south-seeking one. The solenoid also shows polarity. The field lines inside the solenoid form parallel straight lines, indicating that the magnetic field inside the solenoid is uniform.